unmark it, you have to replace the hash dot again by hash, right? So you just overwrite the hash dot by hash. Now this technique of dotting, if you like, or marking, is very useful. It's a very handy technique, so I suggest you use it. You know, it's a well-known device in Turing machine design. Not that many people nowadays use Turing machines for anything. It's well, the theorists do, because you know, theorizing about real machines is so difficult. So that's one of the reasons why the Turing machine was created. It was a paper machine, just created by Turing to basically to solve Hilbert's famous Entscheidung-Problem, which is German for decision problem. How could you decide? You know, what would the mechanics be to decide from a given set of axioms, you know, mathematical number theory or arithmetic type axioms, whether a given statement, like a was how would you derive that statement? You know, prove, logically derive that statement from the axioms. That was the challenge, and Hilbert took it up and thought about it, and out of that came the Turing machine. Right? So the Turing machine was Turing's answer to Hilbert's challenge, and a lot of people took up that challenge. Another famous guy was Church, and Post, and Clean, and various others, mostly logicians. And so, and we'll do it later, the Church-Turing hypothesis, which I won't go into yet. We haven't done enough theory, but it's the same church. Right? Okay, so if you want to mark various characters, you know, like for example, if you want to mark the hash symbol to hash dot, well, you have to add the dotted version of the symbol into your tape alphabet. So that's a general comment. So any symbol you want to dot or mark, you'll have to add that dotted version of your symbol as a separate symbol into your tape alphabet. Right? That's this comment. All right. Now, okay. So we finished more or less the discussion of the 4 examples, and now this is a bit. We've done this a little bit before, and it's still, in my view, still somewhat confusing because a distinction is being made between a Turing recognizable language and a decidable language. And now, is this another case of Sipser's, what for him may be very obvious and it's not so for the rest of us, or is it something that even he, when he was writing it at this stage in the book, he felt would be something that would become clearer later, like especially after we've done chapter 4, the next chapter. So be conscious anyway. So personally, I'm still somewhat confused by this distinction between a decidable language and a Turing recognizable language. Now the 4 languages we've done, A, B, C, E. What happened to D, by the way? We didn't do D, did we? Maybe he's reserving that for something later. Okay. Anyway, these 4 languages we've done. We devised 4 Turing machines to recognize them. These languages were decidable. So they are Turing decidable. Now, what does that mean? So the Turing machines were deciders. A decider is a Turing machine that only has 2 options. It either accepts or rejects. It doesn't loop. Okay? It does not have this third option of looping forever. Okay, so these 4 languages are decidable. You know, Turing, and he just states here, all decidable languages are Turing recognizable. Now, is that obvious? seems fairly obvious. So the question then arises, what's the difference actually between a decidable language and a Turing recognizable language? That's where my question mark is at the moment. Now, is that so blindingly obvious to Sipser that he just states it and expects you to see that it's really obvious, or is it not? But one thing that is obvious is it's just modus ponens. That's just a way of doing logic. Modus, the mode or mean, the way. Ponens, modus ponens. It works in the following way. You're given two bits of information. If A, then B, but you're also given A. Well, then you can use modus ponens to, this way of performing logic, to deduce B. If A, then B, and you're given A, well, therefore B. Right? If you live in Xiamen, you live in China. Well, I do live in Xiamen, therefore I do live in China. Okay, that kind of reasoning. So the same thing's going on here. So these four languages are decidable, they're Turing decidable, and Sipser just states all decidable languages are Turing recognizable. Okay. Well, these four are decidable, therefore, modus ponens, therefore they're Turing recognizable. Right? Well, that's pretty elementary. But the distinction between a decidable language and Turing recognizable, I'm still a little fuzzy on. Right? My question is, what's the difference between the two? That doesn't seem to me too obvious. But anyway, okay. Now, there is a difference because so showing that a language can be Turing recognizable but not decidable, so obviously there's a distinction between the two, is more difficult. See chapter 4. Okay? So this question mark that's hanging over me, and I dare say you as well, hopefully will be clarified after studying chapter 4. Because right now I'm still fuzzy, not clear, about the difference between Turing recognizable and decidable. And when you get into higher level computability theory, there are all kinds of different distinctions made, and this is the sort of you're getting a well, if you follow me for years, I will do a PhD 1 level course. Well, that's the plan anyway, on computability. In fact, I showed you the text a bit earlier. I'll just quickly show you again. You've probably seen this before, but computability, and as you look through it, there are all kinds of different categories of language. So I mean, it's just a foretaste of what's coming. All right. So I'll end there on a question. What is the difference between languages that are recognizable by a Turing machine, hence Turing recognizable, and yet not decidable? That's something to think about. Right, now next session, a whole new section. Right, so we've finished the section on Turing machines, and the next section, so it'll be 3.2, chapter 3, second section, 3.2, and the title of that section is Variants of Turing Machines. In other words, variations. You change things in the basic design of the Turing machine. And effectively, like the main theme of that section is all these variations, or variants, A-N-T-S, of Turing machines, they're all equivalent. Right? That's the essential idea. In other words, they all have the same power. What does that mean? Well, I've done that before. Two machines have the same power if they can recognize the same class, same set of languages. Right? So if one machine can recognize more languages than another, it has more power. Okay? But if the two machines can recognize the same set, same class of languages, set of languages, plural, then by definition they're equivalent. They have the same power. Okay, so that's sort of the theme for the next two sessions.